तो उसको पानी में डाल दिया।
से चल रहा है।
ठीक, so you have started. So you see, steel is in water. And you see what is happening. क्या हो रहा है?
नॉर्मल
पूरा ऐसे प्रोवाइड कर सकते हैं। तो ये तो ज्वाइन कर गया और तो आगे निकल गया।
Moments create हो रहे हैं direction।
You see this? So, what do we prove from this? That we can break steel like paper if you put it in water. कागज की तरह फट गया। So, what is the topic today?
Hydrostatic stress
triaxiality.
No. Stress triaxiality, no. Fracture under the influence of environment. Okay.
Environmental
If
effect।
you don't put water, this still will give you a lot of fracture resistance. Okay. And even if you have crack branching, one of this will lead. Not both of them will continue to grow unless it's a brittle fracture, completely brittle fracture. Then it might shatter. Okay. But in this case, what you saw was both of them will grow in. And then in shear direction, again, two cracks started propagating. And from the video, it was appearing as if the crack came from the underlying surface. वो अवतरित हुआ था, अपीयर हुआ था वो, है ना? पहला क्रैक तो था ऐसा, and then the second one which came like this, that as if it was coming from inside, right? So different mediums can cause corrosion, and that corrosion can degrade the material property to a very high extent. That was evident from this video, right? And so,
सर तो पहले काफी देर तक रखा होगा ना उसमें पानी में।
हाँ, टाइम तो था 2 मिनट।
2 मिनट में corrosion हो
2
गया।
मिनट में corrosion हो गया। So it could be that some materials are very prone to certain media. It's not that if you put this thing under oil, it will not corrode. If you put it in air, it will not corrode, but it has something to do with the salt in the water. So salt environment and sulfur environment and oxygen is usually there at high temperature, which forms oxide. So there are certain media where you cannot avoid going. You can have n number of chemicals. There is no end to what kind of environmental media you can create. But not all of them are interesting for the application purpose. Okay, only those conditions are necessary to be understood where we put metallic materials. And if any other type of material, then in that case you will have to understand the mechanism of that material. So usually how corrosion happens? What's the mechanism of corrosion?
सर iron formation। iron formation।
Iron formation. So there is an electrolytic cell formation. Anode cathode बन जाता है, transfer होने लगता है. So dissolution starts and material degrades. Okay, and then you have similarly you have oxide formation also. But in oxide formation, what happens when oxide forms? It closes the surface in some cases. So further material is not available for dissolution. So Le-Chatelier's principle, if reactants are not available, then there will be no reaction. The other thing is, if you keep on taking the product away, then also the forward reaction will proceed, will keep on proceeding. So if steel rusts, then what do you put? You put chromium in it, which has a higher Pilling-Bedworth ratio. What is Pilling-Bedworth ratio? It's the ratio of the oxide of the metal to the metal. So if the volume of the oxide which is forming, that is larger than the volume of the metal, then the oxide will cover the metal. If it is lesser, then it will not cover, and some part will be prone to the environment, and then the reaction will not stop. Okay? There can be different types of corrosion. There can be galvanic corrosion, there can be pitting corrosion, crevice corrosion, and things like that. So pitting corrosion, when you have pit formation, and this happens in turbine plates in salt solution. So a pit is formed and you have corrosive product there, and this pit acts now as a stress raiser in the material because it has a sharp tip, and that is what was happening. So on these two cracks, the stresses were high. So these high stresses will cause more corrosion to happen there, and once corrosion happens, there will be dissolution here. Okay, and so these two will join together and it became something like this, and then in the shear direction again stresses are higher, so again corrosion started happening in that direction. Okay, so most important, there are a few cases where corrosion assisted cracking is important. One is salt solution. Why salt solution is very important?
Shipping industry is
Conducting nature, sir.
Yes, ship industry. So you have to put a lot of transportation happens via marine, and so you have to put the ships. It has been always the case in war or in business. You always have to put metallic materials in marine environment where sometimes the temperatures are also very low. So material is already brittle, and then you have corrosion, so fracture toughness will go to a very low value or sab toot jayega. Okay. So one is marine environment or salt environment. So, and this salt environment can also be in the coastal areas for aeroplanes, and even when the aeroplanes are flying at a very low altitude on the islands where you have a lot of sea water available. So there was one case which we have discussed in one of the courses. I don't know, Aloha? No, not Aloha.
Aloha.
Aloha Airlines. So it was going from Honolulu to
Aloha.
Hilo Airport, and it used to do a lot of to and fro because the two islands were 600 kilometers apart. So it will just go, and it is a passenger flight. So it will take many turns to generate revenue, and every time the airplane goes up, it is decompressed. It is compressed, and when it lands, it decompresses because of air pressure you have to maintain. So that causes a fatigue cycle, and that fatigue cycle assisted in the salt environment caused the fracture. So the upper body of the flight was just broken and torn away in this space, and one of the air hostess was taken away with it, who was 54, 58 years old or something like that. Okay. And the second important thing is oxygen. So oxide formation, oxidation. This can be combined with 3. because oxidation will happen at high temperature, creep will also happen at high temperature. Creep can also happen at very low stresses. Okay. According to application, this should be either first or second. Hydrogen influence, and then you have liquid metal embrittlement, and you have radiation, but radiation induced cracking is not counted in corrosion cracking. Okay, that's a separate field. Irradiation embrittlement is a separate field. So oxidation, you know that these things will be happening. Hydrogen influence happens because hydrogen is picked up while manufacturing, and the second pickup of hydrogen can happen when you are welding. So when you have covering gases, from that gas hydrogen can be picked up. If you don't have those gases, then oxygen will be picked up. Okay, so hydrogen can come from there. Apart from that, so those are very not very gigantic application areas. Welding is, because anything you want, you have to weld it. But there are various options of welding. Okay, so you can have laser welding, EV welding. Not all the components you can do in that way. But then the majority of the cases are coming because now people are working for hydrogen storage. Okay, and to carry hydrogen from Russia to Europe. Okay, and maybe from Russia to India someday. So how will you carry that hydrogen? You have to carry it in some, either in some container, vessel, pipe, something like that. And what is hydrogen? What is the atomic number of hydrogen? What is the mass number of hydrogen?
2. Let's say 1, it is 1.
Sir, 1, 2 and 3.
1, 2 and 3. Okay. So hydrogen का कितना? I'm not talking about deuterium, tritium. 1. So it has 1 proton, no neutron. So 1 proton, 1 electron. Very easy it is for hydrogen to lose 1 electron. So then what it is? It is H plus ion. What is H plus ion? It's a subatomic particle. It's just a proton. Okay, so any proton is hydrogen plus, isn't it? Because there is no discrimination between proton. Right? So then you can imagine how easy it is to stop hydrogen. So everything should be transparent for hydrogen. Hydrogen can just pass through anything, any container, any metal it will pass through. If it doesn't pass it will at least it will go inside the material. And then why it will not pass? Because it has to interact with the material. If it does not interact, then it is transparent, then it will just vanish. Right? So once you have, and so other areas like welding and manufacturing hydrogen pickup, there you can avoid control in some way. But when you have to store hydrogen or when you have to carry hydrogen, then there is no other option, because you have to put hydrogen there next to it. Okay? And then hydrogen will go inside the material and it will destroy the material. Okay? So we'll discuss about hydrogen, and then the fourth option is liquid metal embrittlement. This happens in some cases where you have liquid metal flowing next to a solid metal. What are those applications? Can you tell one of those? What is sodium?
Liquid sodium.
What is sodium? Is it a metal or non-metal?
Metal.
It's a metal. So in your fast breeder reactor, where is it?
That is inside the vessels.
So it is next to a metallic material.
Yeah.
Yeah. So it is going to cause something. It is going to interact.
With metals.
Liquid metal cooling.
Liquid
Metal cooling applications.
Mm-hmm.
Then you have in fusion reactor, you put lithium, liquid lithium, and liquid lithium, lead lithium eutectic for some reason, because it melts easily. Eutectic will have a lower melting point, maybe because of that. So that lithium is used for cooling in fusion reactor, and it is also used for breeding the tritium which is needed for the fusion reaction. Okay, so deuterium and tritium will combine to make helium, and some energy will be released, and that energy will be released in the form of neutrons, high energy neutrons. That energy has to be harvested, and that is the concept of fusion reactor. Okay, so deuterium you can get from seawater. Tritium is there but not that much, so you have to generate tritium. So tritium can be generated from lithium, right? They are very close in mass numbers, and so lithium is used also for cooling, also for breeding tritium. So in that cases, these liquid metals, they interact with the metals which is containing it. So basically steel in that case, and so it will go inside, and lithium is also smaller inside, so it will diffuse inside and then it will destroy the material. Okay, so alloying elements are good. Hydrogen could also have acted like other alloying elements, and lithium could also have acted like other alloying elements. We deliberately put carbon and nitrogen in the material, right? So why lithium and hydrogen are causing problem, why they are not making it better, I don't know, I'm just asking. And then in radiation, there are areas where you have to put, so as I said, you have high energy neutrons coming out in fusion reactor, and you have low energy neutrons which are coming out in fission reactor. Okay, so in fission, plutonium or uranium is reacting with 2.5 average number of neutrons, and it is decaying, and again the same number of neutrons are coming on an average. You have to control this reaction so that it doesn't become a chain reaction. Okay, so you have control rods. What are control rods? These control rods are made up of those material which can absorb neutrons. Okay, so you have a core where you are putting a lot of rods inside, and those number of rods will make the reactor critical. So calling a reactor critical is that now it is sustained, and this reactor can generate electricity without providing more energy to it. So that's when you call it critical. Before that, when you are providing energy, it is subcritical, then it can become supercritical. It should not be supercritical or more than critical, because then controlling it will not be good. So you always have to monitor the reactor, how the neutrons are coming. You will have to put a lot of sensors, and in some cases graphite is used as moderator. In some cases heavy water is used as moderator. Moderator meaning a chemical or an element which will decrease the energy of neutron to the thermal level, to the equilibrium level or a low level of neutron energy, and there the reaction can be controlled. Okay, so you have to contain the neutrons, you don't want them to go also. Okay, so all those things has to be done, and so these neutrons will now be interacting with the whatever material is there. So it will be reacting with zirconium which is there, it will be reacting with zirconium niobium alloy, it will be reacting with the steel, and of course it is reacting with the heavy water, and that's how it is moderated, right? You also will have to have radiation shielding, where a lot of lead is used so that it can absorb all the neutrons, and you don't have radiation going beyond that. And radiation will also interact with your body. Okay, so we'll not discuss that. So these are the things. So now let us discuss about hydrogen influence. So hydrogen, there is extensive amount of literature available on hydrogen, and still it is not well understood. So a lot of people, including Dr. Mahadan in mechanical, he is working on this area. So hydrogen, there is also a case of hydrogen where hydrogen does not interact in the form of hydrogen, but it forms hydride in some of the materials, and that hydride is stress-induced hydride formation in some cases, and depending upon what kind of hydride forms, the shape of it, that causes problem in the component. Okay. So hydrogen, for hydrogen there has been a lot of theories. So one of the theory is called HEDE, and then you have HEDE. Apart from that, there are other abbreviations and a lot of mechanisms, but very briefly we'll touch upon these two. And so HELP is hydrogen enhanced localized plasticity. So in that case, hydrogen interacts with the dislocation, with the lattice, a unit cell in the crystalline material. And we have, I don't know, have we discussed? We have discussed in MM504 how the alloying elements cause, so in solid solution strengthening, alloying elements can cause strengthening via different mechanisms. So one of the mechanism is elastic interaction, okay? Then you have modulus interaction, then you have stacking fault interaction and things like that. Then you have electric interaction also in ionic compounds. So modulus interaction will happen here, and hydrogen will decrease the shear modulus of the material. By decreasing the shear modulus, it will enhance the plasticity locally, okay? And this local plasticity enhancement will cause softening of the material locally. So this is not going to give you a lot of problems. It is just dropping the strength locally, right? But this goes on hand in hand with HEDE, which is hydrogen decohesion. Okay, and in that case, what happens is that hydrogen causes the material to break because of the decrease in the strength of the material by interacting with the dislocations. Okay, and this goes on hand in hand. So HELP and HEDE will go together, and that will cause problem. There was a previous theory which is called hydrogen trapping. So in that case, the theory proposed was by Tillman, and the theory is that hydrogen goes inside and it forms bubbles. So it acts like a gas, and that gas has pressure. This pressure, so these hydrogens will go to a highly constrained area where hydrostatic stresses are very higher, and they will assemble there. Once they assemble there, then they will have a pressure on it, and this pressure will help in breaking the material, okay? Because this gas pressure will be acting outwards, so it will help in breaking the material, okay? So these are, so we have just touched upon how this thing happens, and you can imagine, because hydrogen is an subatomic particle or in size to that level, you can't say that they are sitting in the interstitial sites or they are sitting in some other gaps or where they are sitting. If there are n number of interstitial sites and you have one hydrogen atom, where do you think that will be sitting?
Moving all around.
At one point of time, where it will be sitting? At a particular time, if there are 4 interstitial sites, one hydrogen atom, will it be sitting? So it will be sitting at one side, 2 sides, 3 sides, 4
One
sides.
side at a time.
One
At
side.
a time.
It will be sitting at 4 sides at all the times, because it's a subatomic particle. So it has a probability to be available everywhere. Okay, you remember Young's double slit experiment? You throw one electron, it passes through both the slits, because it is not only one particle, it is also a wave. Okay, it is in the quantum state. So to find out that how it is interacting with dislocation, quantum state equations has been used. So Dirac-Somebody equation has been used to find out how it decreases the shear modulus and how it helps, or so how it does help and how it does help. Okay, so that's the problem of hydrogen. Okay, so after this, let us talk about normal corrosion environment. Like you can have salt environment, chloride environment, sulfide environment. and you can have oxide environment, and in all those cases there will be electrolytic dissolution, and when you have a crack you have a highly stressed area, okay, and they will be dissolving it, making the new surface available that will get oxidized, for example. So this oxide will close it. It will close the surface because oxide has formed and filling Bedworth ratio is high, so it will close it. So further oxidation cannot happen. Okay, so it should stop. So something will take away this oxide. So this has been observed that when oxide formation happens, then the crack resistance decreases. So before that, let us look at this hydrogen thing. So hydrogen can change to atomic hydrogen, okay, via different processes. So it can lose one electron or it can join with one electron. Both of these things it can do. It can react with a metal and it can form a metal product with whatever X hydrogen is combined with. So it can be H2O, it can be HCl, it can be H2SO4, all those things. So you can have metal sulfate, metal chloride and things like that formation, and hydrogen will be available. And then it can diffuse in the material or it can combine or assemble with the dislocations, okay, and via those it can interact with the lattice by changing its shear modulus. It can go to the grain boundary, make hydrides. It can interact with the incoherent precipitate. It can form dislocation tangles. It can also generate dislocations. Okay, so a lot of hydrogen atom will sit at one place and then that place will collapse because hydrogen cannot sustain the pressure. So it will collapse and you will have a frank partial dislocation appearing there. And it can go and interact with void in pores and coherent precipitate, and some of them will give you a brittle fracture, some of them will give you ductile fracture, some of them will give you intergranular fracture when this happens. Okay, and what do you see in this graph? You see that crack length is being monitored against time, and when this is in humid environment the crack length increases. Okay, humidified argon is there, and then you have humidified argon plus oxygen, so you give oxygen and then the crack length stops increasing. Why? Because oxygen is now closing the surface which is prone to the corrosion. Okay, then you put pure hydrogen and it increases with a very high slope in comparison to this case where hydrogen was present in the form of H2O. Okay, here you have pure hydrogen, then you have humidified argon, and then you have oxygen. Again it stops. When you put water, it starts. So oxygen has been found to stop the corrosion by closing the crack. Okay, but not in all the cases. And then when you do fracture testing, so you calculate K, okay, versus time, and this is dry, so there is no environment, no influence of environment, and then you put the environment and let the time do its thing, and then what happens? K drops, okay, and these are the points which is showing no break, and above this points there are data points which shows that breaks into two pieces. So you do those experiments and then you draw a line at the boundary of no break and break situation, and you can get that above this line the material will break, below this line it's like endurance limit. Okay, so you have a stress below which fatigue failure will not happen. In this case you have a K below which if you put that environment for a very long period of time, even then there will be no influence. Do you understand the meaning of this? I have put the material in chloride, but I don't apply the stress on it. So that first video which you saw, that first video was similar to that. We'll discuss that. So there was some stress on the crack tip. Okay, if there is no stress on the crack tip, then if you put it in water, it is not going to do anything. It is not going to react in some cases. In some cases you will have rust formation, we all see, those kind of rust formation. So for every chemical reaction there is a threshold value of K. If your K is smaller than that threshold value, you will not have any influence on the stress intensity factor, critical stress intensity factor. Okay, and if you are beyond that, then the material is going to break. Okay, so this K1C is smaller than the K1C which you obtained without the influence of environment. If I put my steel in chloride and if I put my steel in ambient environment, in both cases I am getting two different K1Cs. One K1C is telling me that if you go beyond this value in ambient environment, then the material will have a catastrophic failure, right? This value is 180 ampere root meter, let us say. Then you put the same material in chloride environment and this value drops to 80 ampere root meter. Okay, so this is called K1 SCC or K1 EAC. SCC is stress corrosion cracking, EAC is environmental assisted cracking. Okay, so there is a threshold, and this threshold, this K1C, is smaller than the K1C which you get without that environment. Okay, it was found in research that this line is not a fixed line. This KTH value is not a fixed value for certain material. It changes with the patience of the person who is doing the test. Okay, so it is again like that endurance limit concept which breaks when you go for higher number of cycles. In this case also, if you wait for more time and then that more time is not defined, if you just keep it like that, it is going to dissolve at some point of time. Okay, because everything is biodegradable. Like everything is radioactive, everything is biodegradable, even plastic. It just takes a lot of time. Okay, but we are not talking about biodegradability here. This will be a different reaction which will happen. And what is this? So in order to perform this test, you have to do a lot of testing and you will have to generate a lot of data points, right? So you put one sample in the specimen, okay, and this looks similar to the pre-testing equipment where you put a kind of cantilever beam and you put a weight here and then you put an environmental chamber here, and in Crete you had a furnace. Here you have an environmental chamber, and in this chamber either you put the corrosive gas or you put a corrosive liquid. Okay, so for that you will have a container, then you create vacuum here, and this container you have your sample, and here you have corrosive media if it is liquid. When you are doing that, you should be very sure that your fixture should not dissolve or your threads should not dissolve. Okay, so and this figure is so a similar figure has been found in the book of Galileo. Okay, for similar kind of testing, so it matches pretty much. And this picture you can see in the book of Hertzberg. Okay, so for this kind of graph, if you have to generate, you have to put a lot of samples, and you have to, so you put the sample and wait for 1000 hours, or maybe less, 10 hours or whatever is the time t. You wait for time t, and then you see that it is not breaking. Okay, then you leave it there. So you just wait for this to break. Whenever this breaks, you put that point there. Then you keep on doing a lot of testing, and it will have a lot of scatter. Okay, the same material will break at 1000 hours and will also not break at 1000 hours, right? Because every sample will have its own chemical structure, its own heterogeneity, so segregation of inclusions and other things. Okay, so why that sample? Because that sample can tell you the threshold value with one sample. You don't need many samples there, and this is a very easy test. Okay, and we should do it. at some point of time. What is there? And it's a very old picture. This is in the picture of Hertzberg, so it must be from 60s. Okay. So what is happening there? This is a CT specimen which is a little modified. Okay. And in the CT specimen you don't have holes, so you don't have pin. Apart from that, everything is same. Okay. You have a hole from the top, and from that hole, and you also have a hole here on the lower part. So let me draw the CT specimen in 3 dimensions. Okay, so this specimen is something like this, and you have a hole here, and in this hole you have a screw. This screw goes in, and you have some hole here also to a certain depth. It is not through and through. Here it is through and through, not there. So you put a screw and tighten it. Okay. Once the screw touches this end, then you have zero load. Then you tighten it 2-3 threads more, and it will open up. Right. Then you can measure the COD here. How much crack has opened? From that you can measure how much stress has been applied. Okay. So what you have to do, you have to measure the COD, and then you have tightened the screw, just throw it in the seawater. Throw it and keep watching. Okay. After 1 hour you come back and you will see that the crack has grown. And then you wait for 10 years, nothing will happen. The crack will not go beyond this. To ensure that, you can again measure COD and find out how much stress is there, and the stress will be 0. If the stress is 0, then it is not going to grow anymore. Okay. So you started with some K value, and you know how much crack length has happened, crack growth has happened. So you know the amount of delta A, and you know the amount of time it has taken for that much amount of delta A. And from this one specimen, you can calculate KTH, right? Because this will stop at KTH. The stress will not be 0 when you measure that no crack growth is happening. It will be some finite value of stress, and that stress will be giving you the value of KTH. It doesn't have to go to 0 for no crack growth to happen. It will not go to 0. Okay? Because below this, once the stress reaches to this stress intensity factor, crack is not going to grow anymore. If the crack is not growing, you will have no load drop. So the stress will never go to 0. Okay? So whatever COD you get here when the crack is not growing, that is your KTH, and this whole value of KTH you can generate from one sample. Okay, similar things you can do in creep. You just put a screw in the sample, tighten it, and throw it in the furnace. Okay, and you will get the threshold. You can do it for different samples which are starting at different crack tip locations, and you can also see the effect of constraint, in plane constraint, and all those studies you can do. The problem is, there is a problem. The problem is that how will you generate a pre-crack? This is a practical problem. How will you generate a pre-crack? In order to do a pre-cracking, you have to apply a fatigue loading. In order to have a fatigue loading, you have to have holes in it. You have to have pin loading of CT specimen. Otherwise, how will you do it? Okay. So for this specimen, they propose that you, even if you don't have a fatigue pre-crack, it is okay.
So EDM we can use.
The EDM will also not generate that fine.
Yes, that's not fine, but we can use for
For
test.
polymers, you can do it easily, but polymers will have other problems. For polymers, when fracture testing is done, there is no fatigue pre-cracking. You just create a sharp crack with a blade. That you cannot do in metal. And blade is also not that sharp. Okay. but for polymer it works. So in this case, you take a conventional CT specimen, then you do a fatigue pre-cracking. Once you do a fatigue pre-cracking, then you make a smaller specimen out of that, and then you put a bolt there. You do fatigue pre-cracking on CT specimen, make a half CT specimen for this kind of testing. Okay. So then we will discuss this in next week. We have